Hello, everyone. Welcome again to our series on strength of materials. Today we are looking at axial deformations, statically indeterminate problems using the method of superposition. Before we go to our question, kindly subscribe, like, share, hit the notification bell. Let us look at our question for today and how to analyze. Good. A polystyrene rod consisting of two cylindrical portions, AB and BC, is restrained at both. If E is equal to 2 MPa, determine the reactions at A and C. B, the normal stress in each portion of the rod. And we have this diagram. Let us look at how to go about this kind of problem. Good. So we want to see how to solve this problem. This problem is called statically indeterminate because you see that when you draw the free body diagram of this whole structure, you will find out that the free body diagram is going to look like this. And we have the 8 kilonewtons at this side. This is 8 kilonewtons. At this side also we have our 8 kilonewtons. And there will be a reaction according to that test. There will be a reaction here which can be termed as FA. And there will also be a reaction at this where there is a support. So there will be a reaction at A and a reaction at C also. Good. So what we can do, we are going to get a reaction at this side, and it is still called RF. We can call it FB. When you write the equilibrium equation, we are going to get FA going up. So it's positive anytime the force is going up, positive when we are coming down, negative. So from there, we can get FA plus. Sorry for that. So we can be able to determine the structures there. And from there, you can see that FA plus FB minus 8 minus 8 will be equal to 0. However, you can see that we have two unknowns there. And looking at the problem, we don't have any force on the x-axis. We don't have any, we only have forces in the y-axis. And because the forces are having a common line of action, we cannot take moment. So we say that this kind of problem is called statically indeterminate problem because the number of unknowns there, which are 2, are higher than the number of equations. Here we only have one equation and we have 2 unknowns. And if you have two unknowns, you should have a minimum of 2 equations to be able to solve. Therefore, there are 2 methods in dealing with statically indeterminate problems. Is to use the method of superposition. The method of superposition and superposition, and then you can also use the compatibility condition or compatibility equation. But compatibility condition. So these are the two methods you can use to solve statically indeterminate problems. Good. Having been able to say that, we are going to solve this example using this method of superposition. Then we will look at the compatibility condition later on. To solve using the superposition method, what you do is to draw the free body diagram as we have drawn here. I don't have to draw it again. You draw the free body diagram as we had already drawn. And in the superposition method, once you draw the free body diagram, you can write the equilibrium equation. So you say that f of A, just as you also wrote, f of A is going up to a positive, plus f of B is also going up, is going to be positive. Is going to be positive. Then we have the 8 coming down. So minus 8 should be equal to 0. And from there we can see that FA plus FB is equal to 16. This will be our equation 1. Once we are able to write that equation, what we do is that we come to our structure again, and we assume that using the method of superposition, to assume that there is no rigid support at one of the ends. So you can see that you have rigid support at A and rigid support at C. For the superposition method, what you are going to do is that you are going to assume that there is no reaction at this side. There's no reaction. So that is going to be your first situation. So this is point A. You can decide to use the A or you can use the B. So let us try to use the B. Sorry for that. Let us try to use the A and assume that there is no support at A. There is no support at A. So we can draw a free body diagram like this. There's no rigid support at A, and this is the ground. This is the ground. This is the ground. And we have our 8 here. And we also have another 8 here. And we assume that there's no rigid support at A. However, the one at B still remains. The one at C still remains. Then, once you have assumed that, we calculate the deformation. You can see that you only have the external forces being applied on the whole structure. So we determine the deformation as a result of the external forces being applied. And if we want to determine the deformation as a result of the external forces which are applied, we are going to also divide into sections. You can see that the diameter at this section, we said that anytime you have a complex structure, you divide it into smaller sections. Here you can see that this side is section 1, this side is section 2. The diameters are different, and also forces are acting even at this side. So the diameters are different, and we need to section that, and then we determine the deformations associated with that. After we have assumed that there is no reaction or no support at A, and we have calculated the deformation, we are also going to assume that there are no external forces. So we are going to get our structure like this. There are no external forces in the second instance, but the only thing which is there is the support at A, the reaction at the support at A. So this is still our C, which is a rigid support. And in this case, you are going to, in the second case, you are going to assume that there is no external force being applied. So we only have the rigid support at A, and we have already stated that the reaction at A, we will call it FA. Good. So this is going to help us to The first instance is helping us to determine the deformation associated with external forces. So we call that the P. And the second one is helping us to determine the deformation as a result of only the rigid support at A, only by the rigid support at A. Therefore, we can call that deformation the A. So what, after doing that, we can say that because the whole bar is in between the two rigid supports, they are not going to elongate. The total elongation or the total deformation is going to be 0 because it will not allow it to expand beyond this rigid support and also do not allow it to expand beyond this rigid support. So we can say that the deformation as a result of the external force, which is the P, plus the deformation as the result of the reaction at A, when you add the total deformations, they should be equal to 0. It should be equal to 0. It should be equal to 0. But here you can see that the external force there is pushing the material down to point C, which means that it is compressing, and the reaction at A is rather now trying to elongate the structure. Therefore, we can say that the deformation as a result of the external forces is going to be negative. Is going to be negative. So once you have been able to do that, now let us try to determine the deformation as a result of the external force and the deformation as a result of the reaction and the support. So first of all, let's determine the deformation dP as a result of the external forces. So if you want to get the P, we are going to divide this whole structure into two. We have section 1 and section 2. But you can see that at section 1, when you pick this section here and you draw the free body diagram, you can see that there's no force at this side, and the internal force within that section will be P1. Because there's no force up there, we can just say that P1 is equal to 0. And if P1 is equal to 0, our deformation for that side will be, the formula is P L over A. And because P is 0, everything there is going to go to 0. But at the section 2, there are forces there. So at section 2, we are going to get a free body diagram like that. And we have forces acting here. These are rigid support. We have another force here. So when we cut through this section, to our P is going to be down there. So we can call this P2. And this is 8. This is 8. Let us change the direction of P2 so that we sorry for that. Let me erase everything and draw again. So from there, our free body diagram, just as we said, is going to be like this for section 2. Don't forget that when you are determining the internal forces, we said that this is 8, this is 8, and our force there can be called force P2. So from here, we can say that negative 8 is coming down to negative minus 8 plus P2 should be equal to 0. And from there, we can say that P2 is equal to 16 kilonewtons. 16 kilonewtons. And once you have been able to do that, you can calculate the deformation as a result of P2. And that will be equal to P2 L2 over A2 E2. So from there, delta P2 will be equal to P2 is 16 times 10 to the power 3 kilonewton, so times the length of that side. So the length of that section. The section is from this point, section 2 is from this point to that point. And we know that the length is 5. So you have times 5 over the area. The diameter is 500. So we are going to get 3.142. 3.142 times the diameter, which is 0.5 squared, all on 4 times this is 5. And the modulus of elasticity, which is 2 times 10 to the power 6. So from there, our deformation for P2 for P2, sorry, allow me to clean this session so that we can get some space to work the other ones out. So the deformation as a result of P2 is going to be the delta P2 will be equal to 0.204 meter. Then once you have been able to get that, that will be, because we said that P1, the deformation for P1 is equal to 0. So this will be the total deformation for delta P, or delta P. Then now we can calculate delta A, which is as a result of the reaction at A. So delta A2, because you have 2 sections, you have 2 diameters. When you start moving from this side, you encounter a different diameter. We said that when you encounter a different diameter, you divide. So this will be section 1, this will be section 2. So we have to calculate the deformation in section 1 and also the deformation in section 2. When we draw the free body diagram for, so the A, we are going to get the A1, and then we are also going to get the A2 for section 2. So the A1 will be equal to, let us try to draw the free body diagram. So the section 1, if this is FA, sorry for that, this is FA. So what is down here can be P1. So FA will be equal to P1. And we can say that our deformation will be equal to P1 L1 over AE over AE over AE. And from there, our formula is going to give us something like this. So we have P1 is equal to FA. So we can replace P1 with FA. Replace P1 with FA. And the length of that section, the length is 6.5 over 6.5 all over the area, which will be 3.142 times the diameter. We know the diameter to be 350 millimeters, so we change to meter square all on 4 times the modulus of elasticity, which is 2 times 10 to the power 6. And from there, that deformation is going to give us 3.378 times 10 to the power -5 FA. Then allow me to clean this side. Sorry for that. I hope you remember the formulas. Allow me to clean this side so that we can get some space for our work. Good. Sorry for the delay in this. Good. So once you have been able to do that, we can just draw for the second portion of the deformation as a result of this, which is the bigger diameter here. So in that case, our force diagram is going to be like this. We said that there are no, so this will be P2, and our reaction here can be FA. So from here we can also see that FA is equal to P2. FA is equal to P2. And we can write our deformation for this second section here, because that is what we are looking for. So delta A2 will be equal to E2L2 over A2 E2. And from there we can say that our deformation will be equal to P2 from the question is the same as FA. So we can write FA times the length of the second section. So it's from this point to that point, which we are given as 5. 5 over the diameter, which is 3.142 times the diameter is 500 millimeters, so it changes meter, all on 4 times the modulus of elasticity, which is 2 times 10 the power 6. And from here we can see that the deformation there will be equal to 1.273 times 10 to the power negative 10 to the power negative 5 FA. Negative 5 FA. And once you have been able to do that, now don't forget that you have already stated that the deformation as a result of the external forces plus the deformation as a result of the reaction activity should be equal to 0, because this rigid support will not allow the bar to elongate. And therefore, we stated that looking at the direction of our free body diagram, this deformation as a result of the external forces is going to be 0. It's going to be negative. So we are going to get negative. The value for that was 0.204. And delta A, we have delta A1 plus delta A2. So we have our values as 3.378 times 10 to the power negative 5 FA, negative 5 FA. Negative 5 FA plus the other side, the other second one, which is 1.273 times 10 to the power negative 5 FA. And all this should be equal to 0. So from here, when you do the math, you can see that from there we can solve for FA. And FA will be equal to 4386.0, which will be the same as, so we can say that FA So we can say that FA is equal to 4.4, this is approximately 4.4 kilo newtons. And putting this F of A into the first equation we wrote for the free body diagram, the first equation we wrote, you can go back and check. We had FA plus FC was equal to 16. That was equation 1. When we put FA here, we can get FC, which will be equal to 16 minus FA, which is 4.4. And from there, FC will be equal to 11.6 kilonewtons. 11.6 kilonewtons. So that is how to use the principle of superposition to be able to determine the reactions at the support. So we are done with the first question, and the second question we're asked to determine the normal stress in each of the sessions. The normal stress in each of the sessions. So for us to determine the normal stress in each of the sessions, we can say that for AB, so the normal stress in AB, we know that the stress is the force over the area. The stress is the force over the area. So AB from A to B, our force there is our force from A to B, because when you are moving from A to B, the force there is only as a result of the reaction at this side. It's only as a result of the reaction FA, because from A, as you are moving, that you have not encountered these two forces. So they are not affecting the stress in AB. It's only affected by the reaction at the support A. So we can see that the stress will be equal to F over A, and our F will be the reaction at the support A. So the force there is 4.4 over the area, and the area is just the pi d square, 3.142 times B. B is 0.35 for that section, in the millimeter to meters all over 4. And from there, our stress will be equal to 48.8 kilopascal. Then the last aspect is to determine the stress in BC. Determine the stress in BC. To be able to determine the stress in BC, you can see that now from A to BC, we'll be encountering these two forces, these two external forces. So it means that if A is pointing upwards and these are coming downwards, then we need to write the equation for that. So if our free body diagram is like this, this is B from B to C. So we want the normal stress in this section. But the normal stress in this section is as a result of the force at support A and these two external forces. But don't forget that we indicated F of A as going upwards like this. So we can say that the force in this member B to C, the force in the member B to C will be, if you want to get that, we have to get a reaction which is moving up. So we have F of A or you can just draw the free body diagram. So if you want to get the force here, If you cut this side and you want to get the force, don't forget that this is 8, this is 8. So when you cut through the second section, you can get the force as P2. So you can say that P2, let me draw the free body diagram for you to see very well before we continue with that. I want you to get it once and for all. So our structure is like this. And we have a reaction at A, F of A. And we have 8 here. This is also 8. And this is where we have cut, so this side is going to be P2. So we can say that FA is pointing upwards. FA, these two are coming downwards, so minus 16. We already know FA, so we can put in the value. P2 is pointing downwards, so minus P2 equal to 0. FA, we had already calculated FA at 4.4, so we can see that P2 will be equal to negative 16 plus FA, which is 4.4. And from there, P2 is equal to negative 11.6 kilonewtons. And once you have gotten the force from B to C, we can calculate the stress. So the normal stress will be equal to the force over the area. And our force is 11.6 times 10 to the power 3. You can decide to ignore or to bring, but you know the unit. And the other one is going to be 3.142, which is the area. 3.142 times 0.5 all on 4. And from there, we'll be able to determine the normal stress in member BC. So from there, the normal stress in member BC, is equal to negative 59.1 kilopascal. And this brings us to the end of this question. It was a bit detailed, but I believe you were able to understand the processes. Once again, we want to thank you for keeping in touch with us and staying with us up to this time. We appreciate and we say thank you for watching. If you have not yet subscribed, kindly subscribe, like, share, and leave your comments and suggestions at the comment section as well. Thank you for watching. We'll meet again in our next video. Until then, we wish you the best of luck. See you in our next video. Bye-bye.